everyone, welcome back to room 30. I'm Mr. Bullington here with my friend Chip. How's it going today, Chip? Outstanding. All right, so we're going to talk a little bit today about Explore 3 heat and energy, and we're going to focus a little bit on what is heat. Any idea on what heat is? Heat is the transfer of thermal energy from one object to another object. So as that thermal energy moves from one object to the next, that is what heat is. Do you think there's some objects out there that are better at transferring heat from one object to another? So can you name a few examples of substances that would transfer a lot of thermal energy into or out of you if you touch them? Things that when you make contact with them, you can actually feel that transfer of energy. Oh yeah, an ice cube, that's a good idea. A hot stove, sure, that could be it. Maybe like the hair straightening iron you were using the other day, Chip, when you're trying to get your hair straight. That thing gets pretty hot when you touch it, right? Yeah, so things like that. Those would be things that definitely are good at moving that thermal energy around. What do those things all have in common? Any ideas? Yeah, sometimes they're really hot or they're really cold, like an ice cube. Transfers a lot of that energy. Sometimes you notice a lot of those things are metal. Yeah, that's right. So metal is definitely a good conductor of heat, right? So these objects seem to have a lot of thermal energy or a very small amount of thermal energy in them. That those things had in common, right? Yeah, so our investigative question today for this lab that we're going to do, we're going to focus on, it's the top of your page there, and it says, what factors affect the ability of a substance to transfer its energy of its vibrating particles or thermal energy to heat or be heated by its surroundings? So we want to know what things are going to impact this transfer of energy or this heat movement from one material to the next. What you need to do is come up with some kind of hypothesis. What do you think could impact the heat transfer from one object to another? What type of things in our surroundings might impact that? So go ahead and take a few minutes, write that down, and while you're doing that, I'm going to get our lab ready for today. Come on, dude, let's go. All right, you guys, I've been busy while you were answering that question about your hypothesis there, setting up this lab, getting us ready with all the materials. You see there on your paper, you have a materials list. I have the same list here, and I just want to make sure everything on the list is covered, and then we have it all. It asks for 3 stations set up here for our experiment. So I've done that for us. You see here it says 2 beakers, 500 mil. I got those here. 2 thermometers. I have 2 glass thermometers right here. They have a little red stopper on them so they don't roll away. Our safety glove. I have these tongs here to grab my beakers instead of the actual safety glove. And then I have my hot water here, and you can see a little steam coming off of it, and some ice water right here. So there's the first item. Of course, I have on my safety glasses, so important to keep those on. I also have here a graduated cylinder, which I can use to measure out some of the amounts of water. Station 2 right here says to have the safety glove, which I'll use the same one. I do have 2 more thermometers here. I have my 2 beakers, so it says 250 mil beakers. These are 500, but we can put 250 in there. They're marked out. Oh, sorry, these are the ones that we're going to use for our 250. It does say 500 on there, and then it says room temperature water, which I have right here, and then hot water again is in the kettle. The last station here to my right, 1 laser thermometer. So we have these laser thermometers here. I have a couple different brands, and I noticed as I was playing with them, they both give different readings. I was looking at the instructions based on how far away you are to the object or how close you are. You might get different readings. It also says if the surface is glossy or reflective, you might get a different reading. So one of the suggestions was to paint the surface black that you're measuring or cover it in masking tape, which seems really insane to do to try and get the temperature of an object, to paint it all or to cover it in tape. So I don't know how reliable these are, but that is what we're being asked here. I've got my wax paper, aluminum foil, got some sandpaper here, 60 grit, construction paper, as well as 1 ceramic tile from the Home Depot. So I'm going to use this one, but that is what we need to look at here. So a few things about the safety rules, right? It says do not touch the beaker of hot water with your bare hands. It's hot, obviously. Use a heat-resistant glove. I have our tongs here to help me out. Never put cold water in a hot glass. It will shatter. As I was getting these, I noticed this one has a little tiny crack in it, which might be from somebody who didn't follow those directions, but maybe you've noticed that in your house. You don't want to transfer really hot liquids and then really cold liquids in and out of the same containers. It could cause you a problem. Let's see what else is on here just to make sure we cover it. Oh, so that's pretty much our safety procedure. So you guys should be pretty safe in your home behind your computer monitors there, but if for some reason you're not, that's not good. So be safe. But I'll make sure I don't burn you here with the hot water. I won't throw any through your screen, anything like that. So our first step here is part one. We're going to do that right now. It says fill the beaker with 100 milliliters of ice water. So I'm going to take my beaker here and put in 100 milliliters of ice water. So these are actually measured out on there. So let's see, we'll just go here. So this will be my ice water on the left. I'm filling it right to 100. There we go. That looks right at 100 there. And then it says, carefully using a heat-resistant glove, fill your second beaker with 100 milliliters of water. So I have this here. I don't really need a heat-resistant glove because I'm using this kettle, which is already heat-resistant. But I am going to add my 100 milliliters in here, and you can see the glass fogging up there. A little condensation on the inside, right? So there's our water. So we have our ice-cold water and our warm water. Now what does it say to do next? Using to place both beakers at your lab station and a thermometer in each one. So I'm going to take my thermometer here, add that to this one, add a second thermometer right here to this container right here. Wow, I do not know if you can see that, but the red line is shooting up on this one here. So that red dye that's in there is moving up pretty fast. Measure the initial temperature of each liquid in Celsius and record it on your data table. All right, so 0 minutes right now. Let's see what we got. These are set in Celsius already. So looking at this, it looks like it is 11 degrees Celsius. So my data table here, I'm going to make one up for you guys on the board so you can see what's going on. So that first one is 11 degrees, and then this one is 70 degrees. Okay, so here's cold, here's hot. 11 degrees Celsius. Is that what we said for the first one? I'm sorry, you guys. Yeah, we did. And then the second, the hot one was, I don't know what it was, but we're gonna do 75 degrees now. So there we go, 75 degrees, and this is all in Celsius, of course. So this is at 0 minutes. And then we have a chart there. It says 3, 6, 9, 12, and 15. Okay, Chip, you got your timer ready? Chip, come on, buddy. Okay, let's watch the clock. 3 minutes. Even though we've kind of already started, we probably should have that timer going. That's okay. I'm going to step off here just for 1 second to grab my timer. I don't have one. Okay. I have a clock on the wall though, so we're going to wait and then we're going to check the temperature and fill that out. So every 3 minutes we're looking at this to see what happens. Sorry, I'm a little confused up here looking, but I do know what I'm doing. So 11 degrees Celsius, I'm just writing this on my chart too so I have it. Okay. Perfect. Got about 1 more minute before our second measurement. And while we're doing this, let's take a look at some of these questions. It says, describe the motion of the particles and the amount of thermal energy in the boiling water, cold water, and the air. Which substances particles were vibrating most, which were vibrating the least? So out of our cold water here and our hot water, which particles do you think would move around the most? Which would move around the least? Take a moment, think about that. Maybe talk to somebody in your head about it. Maybe you can talk to your teacher in your breakout rooms about it. But think about that for a moment. That second question says, describe the energy transfer between the water and the air. So there's air in this room. The air right now in this room is about 70 degrees according to my thermostat, just in case you were wondering about that. But so the air in here is going to have some kind of impact, right, on this water. So take a look at that. Given enough time, would these fluids reach the same temperature? Do you think if we left these here for long enough, would they reach the same temperature? That's an interesting idea. And then does the temperature of the substance affect its ability to heat or be heated by its surroundings? So those are the questions we should be thinking about. Let me check my timer here. Perfect. So let's take our measurements and start the next 3 minutes here while we're doing that. So for my second 3 minutes, this is about 62 degrees, it looks like. So the hot water, oops, I'm not going to use green because it's too hard to see. 62 degrees. And then our cold water here, our icy water, what were you going to be? It's a little tricky to see this one. It looks like it's 11 degrees. Didn't change too much. So there's that. I didn't see any change in there. All right, so as we're going through this, this is a great chance for you to think about what's happening with those questions. While you work on those, we're going to speed up time probably a little bit and see if we can't zoom through these last 3 sections here. And then we'll talk about the next part, which is part number 2 of our lab.
A few minutes later.
Leave them all.
You just said Twitter.
Ah. Looks like 13 degrees still. Almost 14, so we're gonna go 14 degrees. And you, my friend, are at 41. Okay, those are the measurements you're gonna use. Make sure they're on your paper. And Chip, did you wanna add anything? Yeah, do that too. Okay. Part 2, thermal energy and heat. It says place 200 milliliters of room temperature water into beaker A and B. I have my room temperature water here. So we're gonna do 200 milliliters. Ooh, this is just barely gonna work because I had 400 in this glass. Well, that's good. So here's 200. Is that 300? Yes, it is. Let me fix this. So these beakers measure from the top down on this one, or the other one it doesn't, but okay. 200 milliliters room temperature water. We're gonna say this one here is our A, this is our B, all right? Measure the temperature of the water in each beaker in Celsius and record it in your data table. So I have these thermometers here. These are not the ones I just used in the other one, so they should be kind of reset, I guess you could say. And the water's pretty close to the temperature in the room, considering this water's been sitting out in the room for a while, right? So that would make sense. Let's see here. Looks like we're getting 22 degrees Celsius. So measure the temperature, record it in my data table. So the room temperature water in here is about 22 degrees Celsius. So I'm gonna say about, little squiggle there. I think it's a little higher than that, but I can't tell with the fractions on here, so that'll be fine, 22 degrees Celsius. Okay, gather hot water in the larger beakers, placing 50 milliliters in one and 150 in the other. Oh no, did I put these in the wrong containers? I did, because I didn't read the directions. We're just gonna do a quick little transfer. Not good science, people, to do it this way. But for the sake of expediency, I'm gonna do it. Okay, back to my hot water. I had to heat it up again. Okay, good. Hopefully those aren't too cold. I don't want them to crack. Measure the temperature of both, oh sorry. Gather hot water in the larger beakers, 50 milliliters in one. So 50 milliliters. I'm gonna, I can see it a little bit. It's hard with the condensation. Okay, so B here has 50 milliliters and 150 in the other. Okay, so this is our A, 150 milliliters, B, 50 milliliters. Measure the temperature of both beakers of hot water and add that to your data table. Okay, so oh, wow, it's shooting up, shooting up. Let's see. What do you think they're gonna be? Just pulled them off that kettle. Pretty much the same. What? They're not the same. This thermometer. See, we're using real thermometers because this IR thermometer is not showing me a very accurate number here. Okay, so it looks like we got about 75 degrees Celsius, which is a little cooler than I thought, but Guess it's better than burning myself. Okay, 75 degrees Celsius. About. It says make a prediction. When you set beaker A into the beaker with 50 milliliters of hot water, set beaker B into the 150 milliliter hot water beaker and wait 5 minutes. Will the temperature of water A and B be the same or different? So A here, I'm gonna flip them around because it wants A to be the 150. So A here, A to be the 50, sorry guys. A, right here, we're gonna add this beaker, we're gonna set it in there, and then it's saying, do you think, we're gonna wait 5 minutes and see what happens. And in the meantime, you're gonna make a prediction about what you think is going to happen to that water in there. So how do you think the temperature is gonna change in our room temperature water after we set it in the hot water? And A has less hot water than B. So do you think the amount of hot water is gonna impact how much the temperature changes in these? Does that make sense? I hope so. A had the 50 milliliters of hot water. We've set our cup in there. B had 150 milliliters of hot water. We've set our second beaker in there. We're gonna check the temperature on those in exactly, how long did it say? 5 minutes, not 15 minutes, 5 minutes. Make a prediction. What do you think is gonna happen? 5 minutes. Chip, can you watch the beakers? I gotta do something. They're right there. Okay, thanks. Okay. All right, I'm getting for a second. Okay. Sorry guys, I'm trying to do too much. Won't let me type in the box. I'm not even copy paste. Oh good, so everyone's got those problems handled. I don't see any new things going on. This is great. Oh yes, Mr. Macias, what can I do for you?
I went to the bathroom without asking. Is that okay? Am I in trouble?
Yes, you're in trouble. Do 20 push-ups.
Alright.
No, don't do push-ups. No, you guys, you're at home. Go to the bathroom whenever you need to. You don't need to ask. I appreciate you considering that, but if you need to grab, a quick drink or go to the restroom, just do that. It's fine. You're not interrupting class by doing that, because nobody knows, other than if you tell us and then interrupt us with your message.
I have a question, Mr. Bullington.
Yeah.
So for number 5, it says look through each type of substance on the simulator.
Right.
So it says notice a difference between them. But do we look at all of them and add pressure and see how they react, and then write that down?
Yeah, it's saying just look at the different substances and see how they look. You don't even have to add the pressure part. So it's just saying, look at each substance in the simulation, notice the differences between neon and argon and oxygen and water. Why do you think they are represented differently? So when you look at the neon and argon atoms, they're gonna look different than water and oxygen. Why do you think that's the case, is what it's asking. So take a moment and look closely at them and see what the difference is.
Like as a solid, like as I first click on it, or
Just as the actual molecules and atoms themselves.
as the size and color?
Yes. The color shouldn't change for sure, and the size, but just the way they're made up, I think, is more what it's looking at.
Right.
Like some of those are made of multiple atoms and some are made of individual atoms. Yeah, Erica, that's fine. If you guys need to close your camera because it makes your stuff better, that's fine. I'll just be here alone in my classroom looking at black boxes with names. All right, you guys, 5 minutes is up. Let's see what we did. Beaker A. Mm, 26 degrees Celsius. 26. And let's see what Beaker B came up with. 34 degrees Celsius. All right, you guys. So, was your prediction correct? You made a prediction. Was it correct? Did you see the same thing happen that you thought would? Why do you think the temperatures change differently? Why do you think container A, which had less water in it, changed less than container B, which had more water in it? Why would that happen? I know. Well, we're trying to teach these guys. Okay. A couple more questions on there you're going to answer. Think about what they say. And then we're going to move on to part 3 in just a moment. All right, you guys, here we go with part 3, the last part of this experiment having to do with conductivity and heat. I have these 5 materials out here. What we need to do is rank them from which feels the coldest to which feels the warmest. This is just kind of based on our own touch and our own observations, not measured in any type of way. So what would be really great is that you're at home, if you have a few different surfaces around you, to touch them and compare them. Like if you're sitting in a chair with metal legs, maybe grab the legs, or wooden legs. The surface of your table, maybe the piece of paper. If you have a few different substances around that you can touch, see how they might feel as they feel a different temperature, even though they're in the same room. We're all in this room. We, meaning me and Chip, are in this room. The thermostat's on the wall says it's 70 degrees. So I would think these things would all be about that same temperature, but when I feel them, they don't seem to be. So we're gonna check that out. So we're gonna make a guess. Why don't you go ahead and make a guess too and see what we come up with, and then we'll measure these temperatures. So I'm gonna put my hand on each one, see which one I think feels the coldest. Which one do you guys think would feel the coldest? Oh yeah, this ceramic tile definitely feels coldest. You get to be number 1, ceramic tile. That was the coldest. And then the aluminum foil was definitely a close second there. Okay, the other 3 now, let's see. I think this wax paper is gonna be my next one. These two feel very similar. I'm gonna have to, I don't know. Maybe wax, the sandpaper is a little cooler. It's kind of tricky, but that's what I came up with. All right, now we're gonna use this IR thermometer. And I mentioned earlier, it's not really that, I don't feel that it's that accurate. Maybe I'm wrong, but it was different than the other one I had. So the thing is that it's gonna measure all these the same way because I'm going to measure them. I'm gonna use the laser the same way from the same, hopefully about the same distance here. So let's start here with this first one. Take it a couple times. Okay, it says 22.2. That says 22.2. That says 22.2. That says 20.0. That one says 22.2 also. That's funny. They're all pretty much, 22. This construction paper was, I think they're all 22.2. The construction paper was a little bit less, but I'm gonna put 22 degrees up here for all of these. And I do believe, let me just check this one more time. What did I say? This one was a little less, wasn't it? Yeah, so these were all 22.2. The construction paper was 22, so it was a tiny bit less, but I'm not gonna put the decimals up there. All right, so these 5 materials all feel like they have different temperatures to them. According to our thermometer, they're all the same. What? How could they all feel so different? This ceramic tile definitely feels colder than this black paper. Why is that? There's some questions on there that you're going to want to try to figure out the answers to. Why would these materials that all seem to be the same temperature according to our measurements feel like they have different temperatures? You're going to want to go through here and do this a little data analysis, and it explains a little bit about why that is happening. And as you go through these, complete them, and then you're going to go look at your the plastic particle bottles. They're not plastic, the particle bottles on Stemscopes, and do that last part. So that's what we need to do today. Part 3. Chip, anything you'd like to say? All right, Chip, we'll keep that in mind for next time. We'll see you guys next time. Have a great day.